By the end of the episode, you'll know how to safely get out of every single possible situation by simply knowing how to leave Earth. Currently, the only way for us to lift our squishy human bodies off the surface relatively safely is to do so on board chemical propulsion rockets. Chemical propulsion rockets is just a fancy name for the regular rockets you may know, such as Space Shuttle, SpaceX's Falcon 9 or Falcon Heavy, or even the mighty Saturn V. All of them, in all their glory and ridiculously precise engineering, rely on a rather simple concept. But to understand it, first we need to make sure everyone understands the third law of motion. The basic concept is, we take two objects, for example this lid from my marker and my finger, and we exert force by one body on another body. So in this example we're gonna press my finger against the marker, and technically I'm just pushing the marker, right? Well, the thing is, the marker is also pushing back on me, leaving a mark. So to the letter of the third law of motion, if one body applies force on another body, the body that the force is applied to applies the same but opposite in direction force to the body that originally applied the force on it. So for example, if I press down on the lid of the marker with the strength of 1 Newton, the marker is also pressing back down on me with the same exact force of 1 Newton. Quite simple, right? Well, it gets even simpler if instead of talking about pressing on things, we'll talk about throwing things. When I threw the marker, I applied force on it by pushing it away from me. But according to the third law of motion, at the same time as I pushed the marker away from me, the marker has also pushed me away from itself. Obviously, the force applied back on me by the marker is negligible and here on Earth completely unnoticeable because of friction between me and the surface I'm standing on, because of the force of the gravity, because of the air resistance. But nonetheless, if I were to do it in a vacuum of space, throwing the marker would have slightly, but still, propel me in the opposite direction. And this is precisely how chemical rockets work. Very similar scenario was brilliantly demonstrated by astronaut Karen Nyberg, who on board the International Space Station has set her whole body in motion using a single human hair. And this is exactly how chemical rockets work, just on a slightly bigger scale. The basic idea is to have a tank full of something that will throw out the back of the rocket in order to, using the third law of motion, receive the same force with opposite direction in order to build up our speed. This is not only going to work, but also we can prove it from the comfort of our homes. Simply go to the bathroom and turn the shower on. Notice how with the change of water pressure, the shower head will either rise or fall back down. The higher the water pressure, the more water the shower head is pushing away from itself, in result pushing itself away from the water as well. Third law of motion at its finest. But back to our rocket. The problem with this concept is that no matter how much of the propellant we will take with us, if we simply keep throwing it out the back like the shower head throws away the water, we'll run out of the propellant fairly quickly. The easiest solution will be to simply throw less particles at once, but accelerate them to greater speeds in order to keep the force the same. We can see it very clearly on an example of a 9mm pistol bullet. Even though it weighs much less than a glass of water, the velocity at which it leaves the gun barrel is so great that the force applied back on the gun by third law of motion is enough to sometimes flip the gun out of shooter's hands. So now we know that we want to disperse the particles and propel them as fast as we can. And it just happens so that the easiest way to split an object into multiple particles and accelerate them to great speed is by creating an explosion. The only problem we have with explosions is they're quite chaotic in their nature, and if we explode something, the particles will be emitted in all directions. And if our explosion propels particles away in all directions, by third law of motion, the same forces will be generated back into the center of explosion, in result getting us nowhere. So we need a combustion chamber which will trap all the particles going in unwanted directions and will let through only the particles which are following the direction we want them to go to. Some of the particles will remain trapped in the combustion chamber, but most of them will ricochet their way out of there. And now you see another problem is that we have two particles, one going downwards and one being slightly offset, once again pushing us out of the ideal path we want to follow. Especially if we get more and more particles which will ricochet out of the combustion chamber in uncontrollable direction, we'll end up losing the trajectory we want to follow. So we need something that will guide the particles in the correct direction after they leave the combustion chamber. And that's exactly what the engine nozzle is for. So once again we end up with a working design that this time I do not recommend to try at home. But, for example, fireworks. They burn their propellant and they eject the particles down the paper tube, which makes for a rather basic and simple nozzle. Or if you want an example of how a nozzle can direct the particles towards a single place, just look at a fire extinguisher. The longer the nozzle, the more precise the stream. The shorter the nozzle, the more chaotic and undirected the stream of the foam will be. But there is another problem with our design that will hold us from going into space. As you can see from this rather basic formula, to turn our fuel into energy needed to propel our rocket, we need boom and we need oxidizer. We have boom by here, and when we're on the ground level, we have oxidizer in form of oxygen everywhere around the rocket, so there is no problem igniting it. But the higher we go, the less oxygen we have available, because the air around us becomes less and less dense. And that's the exact reason why airlines operating at altitude of around 10 kilometers are always pressurized and they have oxygen masks on board in case of an emergency. There just simply isn't enough air and oxygen in the atmosphere. Neither for humans, neither for our boom reaction. Solution to that is as simple as it gets. We don't have enough oxygen around us, let's just take it from the ground with us. And this is exactly what every single chemical propulsion rocket looks like. Whether it's Falcon 9 from SpaceX, the Space Shuttle, Delta Heavy, or the mighty Saturn V, which again, if you haven't seen... Okay, so we have our rocket sitting here on a launch pad. Obviously none of it is to scale, but let's try to launch it and see what happens. So here we go, 3, 2, 1 and lift off, and we go up and up and up and up. And we have left the Earth's atmosphere, so we cut our engines. And what do you think is going to happen? A, because we are no longer in Earth's atmosphere, we will just keep floating around in the vacuum of space. B, because Earth is going around the Sun and we are no longer connected to it, unless we keep our engines on, we will simply be left behind. C, we will fall back down to Earth because no matter how far we are, the gravity still applies. The answer is obviously C. How did that happen? You see, no matter how much of a down-to-earth person you consider yourself to be, in the eyes of Mother Nature, you are pretty much down to earth your whole life thanks to the force of gravity. Force of gravity described by this formula means pretty much that any two bodies with mass, so pretty much everything in the universe, will attract each other with a force equal to their mass multiplied by gravitational constant divided by squared distance. Which means the heavier something is, the more it is likely to attract other objects. That's why, for example, Earth is attracting you to it, but you are not attracting anything to yourself. That's because Earth's mass compared to your mass is so ridiculously higher. And because all of this is divided by r squared, which is for distance squared, the further away from each other the objects are, the weaker the gravitational force between them. Yes, the force decreases, but still not enough to just keep our rocket casually floating in space. Let's assume the highest point of our trajectory was 150 kilometers. At 150 kilometers altitude, this force of gravity is pretty much the same as down here on Earth. At 400 kilometers of altitude, which is the operational altitude of International Space Station, astronauts experience 89 to 90% of the gravity we feel down here on Earth. So, how does it happen? How is it possible that the International Space Station doesn't just fall back down to Earth like our rocket did, and that the astronauts on board are weightless? To understand that, first we need to know what's the exact gravitational force of the Earth. Luckily, we don't have to do any math because smart person named Sir Isaac Newton already did all the math for us. Thank you, Sir Isaac.
You are welcome.
What? The acceleration resulting from the Earth's gravitational force is 9.8 meters per second squared. Sounds complicated, but it's very simple. It just means that any object in freefall will accelerate by 9.8 meters per second by every second. So within the first second it will travel through 9.8 meters. During the second second it will travel 20 meters, and so on and so on. By the fifth second it will be going at 50 meters per second until it either crashes back down to Earth or will meet its terminal velocity, which is topic for a completely different video, but in short, it's a maximum possible velocity for a free-falling object in the Earth's atmosphere based on the object's mass, surface area, and the air density around it. But let's go back to our rocket. As soon as we cut the engines when we've left the Earth's atmosphere, we started coasting, but gravitational force of the Earth started taking away all the velocity we have gained by accelerating our rocket on the way up. So 1 second after we've cut the engines, we have slowed down by 9.8 meters per second, 2 seconds later by 20 meters per second, and so on and so on. At top peak of the altitude, which is called apoapsis, our velocity got eventually nullified, and we started falling back down to Earth, accelerating at this exact rate. But once again, why doesn't the International Space Station fall back down? And how do we get our rocket to stay in space? Introducing one of my favorite thought experiments, Newton's cannon. Imagine yourself standing on the surface of the Earth. Obviously this is not to scale, but just a representation of an idea. So imagine you stand on the surface of the Earth and you throw a marker. The marker will follow a trajectory and will fall down to Earth. Right, so now let's try the same with a blue marker, but let's throw it a little stronger. Because we have put more force into the throw and the marker was more accelerated horizontally, it has traveled further. So let's do it again. Let's throw another marker, even stronger. Obviously, it will fall even further away from us because we threw it stronger and we've put more energy into it. But let's not stop there. Let's throw it even stronger. As you can see, we have accelerated our marker so fast that it landed in a spot we couldn't actually see. And that's, by the way, how intercontinental ballistic missiles work. This way you can hit targets that you don't even see because of the Earth's curvature. It is quite scary if you think about it, but it has also enabled scientists to see what happens when you accelerate the rocket even further. And so, following this logic, if we throw our rocket hard enough, at this velocity, the curvature of the ballistic trajectory of the marker we threw is equal to the curvature of the Earth underneath, meaning the marker will travel all the way around the Earth and eventually... Oh shit! And this way, the marker has entered what is known as an orbit. Right, so what speed are we talking about? Because definitely everyone would like to try that at home. Sounds like hella fun. Well, the orbital velocity of Earth at 150 kilometers is 7,800 meters per second. But this is a rather abstract number. What about units that we know and use in everyday life, like miles per hour or kilometers per hour? 17.5 or 28. 17,500 miles per hour or 28,000 kilometers per hour. That's how fast something has to go at the altitude of 150 kilometers to keep falling, but never fall. Obviously, if you try to pull it off in the Earth's atmosphere, the friction coming from the air at orbital speed would be enough not only to set the marker aflame, but to vaporize it in an instant. To avoid this problem, rockets take off vertically, and as soon as they are out of the densest parts of the atmosphere, they start turning horizontally. You can often hear a call out, vehicle is pitching downrange.
Vehicle is pitching downrange.
That's exactly when the vehicle starts moving more horizontally rather than vertically, and proceeds this way all the way till it leaves the Earth's atmosphere. At this point, rocket has been burning its fuel for 2.5 to 3.5 minutes, and what it had in terms of fuel and oxidizer has depleted. We could obviously increase the amount of oxidizer and fuel we're taking from the ground, but that would mean more mass, so we would need a more powerful engine. And more powerful engine would require more fuel and oxidizer. Do you see the problem here? This problem is well known to the rocket scientists and is known as the tyranny of the rocket equation. I could bore you to death with math that goes behind it, but essentially it's all about the right balance between the amounts of fuel and oxidizer we take with us, to the power and mass of the engine, to the mass of the payload, so that we don't end up in a paradigm of taking with us infinite amount of fuel and oxidizer that won't be able to take off the ground because of its own mass. The much simpler reason is to design a more powerful first stage that will get us out of the dense parts of the atmosphere, and a lighter, more economical, you could say, second stage, which essentially is just a second rocket stacked on top of our first rocket, which will carry the payload all the way to its desired orbit. So essentially the first stage takes us out of the Earth's atmosphere and sets us on the basic trajectory we want to follow, and after that we can often hear a call out, "Stage separation confirmed."
Stage separation confirmed.
Which means that the second stage has been released from the hold down clamps on the third stage and has ignited its own engine, which continues to accelerate the payload towards its target orbit speed without having to carry all the excess weight of empty fuel tanks and engines from the first stage. Also, the engine on the second stage can be then more optimized to work in a vacuum of space, a smaller, less powerful engine that will be able to run for a longer period of time using less fuel and oxidizer. The payload fairings, which are essentially a protective nose cone, which protects the payload during the ascent from the mentioned air friction, it can be jettisoned, as in the vacuum of space it's no longer needed and it's just an excess weight. Now remember what we said about air friction in the dense parts of the atmosphere and things vaporizing? Well, essentially that's what happens to the empty stages and rocket fairings. Most of their parts either burn up in the atmosphere or crash down into the ocean, where they sank right to the bottom. Cool fact: first stage of Saturn V rocket, which carried Apollo 11 mission to the moon, has survived the re-entry of the Earth's atmosphere and has crashed down to the ocean, where it sank to the bottom. It has waited patiently for almost 45 years to be found and partially recovered by no other but Amazon CEO Jeff Bezos. He managed to recover 2 out of 5 mighty F-1 engines, one of which is now on display in National Air and Space Museum in Washington, D.C. But back to the International Space Station. The reason it doesn't fall back down to Earth and why astronauts on board are weightless, again, not free of gravity, not in zero gravity, weightless. Both International Space Station and people on board are zooming across the sky at 7,670 meters per second. That's why all the pictures come out so blurry, and that's why it takes some serious astrophotography gear to be able to capture International Space Station in its full glory. And the reason why astronauts on board are weightless, again, not free of gravity, not in zero gravity, but weightless, is because they're moving at the same exact speed as the International Space Station. That's why they appear to be weightless, whilst in fact they're in constant freefall around the Earth with nothing like air or ground in their way to stop or slow them down. And that's it in today's episode. Thank you all for watching. Before you go, be sure, if you have any comments, please leave them in the comments below, whether it's if the vaccines cause autism, or how to return from space, or if humans actually were on the moon. please leave your comments down there and I'll make sure to answer them as good as I can. Also, if you have enjoyed this type of content, please make sure to subscribe. We're almost at the 100 subscriber gate, which is going to be a great milestone for the channel. And if you have enjoyed watching this video, please consider leaving a thumbs up below and sharing this video with your friends so that the channel can grow. That's all from me. Thank you all for watching. I'm Alex and you're watching Dr. Gibberish.